Good evening, physics friends. It's your old pal Sean Lally here, and our special business tonight is something called frames of reference, or what you see sometimes depends on how and where you are measuring it, also known as Galilean relativity, not to be confused with Einsteinian relativity, which is the special business of space and time acting together conjointly and moving at incredibly high speeds, something 10% the speed of light or greater. We're not going to talk about that right now. We're getting into something a little more down to earth, these so-called Galilean relativity frames of reference type experiments. So, let us start off with a little query. What, in fact, is relative motion? Well, relative motion is motion with respect to some reference frame. Now, in physics, we almost always have to choose a frame of reference in which we can measure things. Things, in fact, can get strange, however, if we put a reference frame in motion, or if another way to say that is to say that if a reference frame is in motion relative to another reference frame. But of course, as we're going to see, all reference frames are in motion relative to something else. Let's start off with a classic kind of thought problem, a moving walkway problem. I want you to imagine going out to the airport and getting on one of those moving sidewalks. And let's say that this particular moving sidewalk is moving at 2 meters per second relative to the ground or the airport floor around it. So it's moving at 2 meters per second to the right relative to the concrete of the airport floor. So what's the speed of the person who just happens to be standing there minding her own business moving on the moving walkway? Well, the speed of her is what? Think about this for a minute. Well, she's moving. Or is she? Here's where it's tricky. So if she's just standing there, she's not moving relative to the belt, but she has become basically part of the belt. So she and the belt are moving at 2 meters per second to the right. Okay, that kind of makes sense, because after all, if you were standing or sitting watching her, you would say clearly she is moving to the right. Let's make things a little bit stranger. Let's put a little puppy here. Now, this puppy is running 8 meters per second. That's a really fast dog. I think I went over the top here. But this puppy is running at 8 meters per second to the right on this moving walkway. What's the speed of the puppy relative to the ground? Well, how do we deal with this? The puppy thinks it's moving, it's running along on this moving walkway. In fact, the puppy may not even realize it's on a moving walkway, if you think about it. So, puppy's moving at 8 meters per second. The belt, relative to the ground, is moving at 2 meters per second. Now, that 8 meters per second is the speed of the dog relative to the belt. But the speed of the puppy relative to the ground is the combined speeds, 10 meters per second. Let's say, for example, now that the puppy turns around, starts going at 8 meters per second to the left. Well, the belt is still moving at 2 meters per second to the right, so what's going to be the speed of the puppy relative to the ground now? Think about this. They're moving at 8 to the left. Belt still moves at 2 to the right. Sure enough, they're moving now at 6 to the left, which is the difference between 8 and 2. 6 to the left. And if you prefer to think in terms of... Oh my goodness, what's going on here? Sorry about that. If you prefer to think in terms of negative numbers, then that is going to be negative 6 meters per second. Oh, maybe it's a little annoying, of course, or it's adorable. I think it would be adorable. You decide. Okay, so another thing to think about here, what would happen if the dog were moving at 2 meters per second to the left, while the belt moves at 2 meters per second to the right? Well, first of all, I need to be a little bit more specific. If I say the dog is moving at 2 meters per second to the left, I really need to specify that he's moving with respect to the belt. So, if the dog is moving at 2 meters per second to the left, relative to the belt, as the belt moves 2 meters per second to the right, then the relative speed of the dog is 0. In fact, it's running in place. But you probably knew that, because that's what a treadmill is. You've probably been on a treadmill, or at least seen one before. So a treadmill runs at a certain speed that you choose, and you run in the opposite direction of the treadmill, so that you really never get anywhere, but you're still able to run in place, exercise in a short amount of space. Kind of convenient if you think about it, and really just exploits some frames of reference classic physics. Okay, now at this point I have a couple of links to video clips right here. So you can actually follow along in the PDF of the notes and then take a look at these two clips. The first one's very short. It's just about a minute. It's from Mythbusters. And the second one is a good bit longer. It's 5 or 6 minutes. It's from Saturday Night Live. The first video is a Mythbusters clip, and it shows what happens when you fire a ball out of a moving truck. So they are moving. They have a pickup truck that's going at, I think, 60 miles per hour to the left of the frame, and they fire a cannonball at 60 miles per hour in the opposite direction. What would happen? Now, the second, and that clip is from, I think, about 3 years ago. It might be from about 2017 or so. Now, the Penn and Teller clip is much older. It goes back to the 1980s, but it's such a fantastic clip that I just love showing it. It's a Saturday Night Live clip, and so the quality, the video quality it's a bit bootleggy. It's not the highest quality, but I want you to watch it, and just watch what happens. You'll see that there's a lot of laughter going on. They're doing some sort of what seem to be kind of simple magic tricks, and it's just, I don't want to tell you too much. I want you to think about it while you watch it. Okay? So we're going to take a little break here. You should stop this video, go to the PDF of the slides, and then click on the links so that you can actually go and watch these two clips. Okay? And we'll come right back in a couple of seconds. At least I hope you come right back in a couple of seconds. Okay, well, what did you think of those two clips? The first clip, you saw that the ball dropped straight down. The truck was moving to the left at 60 miles per hour. The ball was shot to the right at 60 miles per hour. And those two speeds exactly canceled each other out since they were simultaneous on the same body. The ball, after all, was still moving at 60 meters per second to the left as it was fired. And it doesn't just suddenly go from 60 meters per second to the left to 0, or it doesn't just suddenly go from 60 to the left to 60 to the right. So the two speeds are uniformly combined, and that gives you a total speed, a net speed of 0 miles per hour. But in the Penn and Teller clip, it's a good bit stranger. You find out by the end, or maybe you guessed earlier, that they happen to have been upside down. It's a completely inverted reference frame. It was completely upside down relative to what you would expect. Now, that's probably why everybody was laughing so much, because they knew the joke was kind of on the TV audience. But if you can, go back and watch that clip again and look for the tells. Look for the things that now tell you that indeed they were actually upside down the whole time. There are a few. If you watch the playing card moving and leaving Teller's hand and going up, look at the shadow of the card. You can see it move up his shirt. That is a little bit obvious now, but then you can tell, you get a sense of sort of what's going on there. Also, if you move it slowly, you'll see that it is indeed accelerating. It's not just going up at a constant speed. The other thing I think that is way more obvious now that you think about it is when they unscrew the light bulb from that hanging light fixture. And or that floating light fixture, I guess I should say, even though it's obviously hanging. Now we know it's hanging. When they unscrew that and they toss it from hand to hand, when Penn tosses it from hand to hand and through the ring, it takes an upside-down parabola, takes an upside-down curve, which is, of course, the exact opposite of what it should be when you throw something from hand to hand. It doesn't go down, it goes up. Okay, so if you get a chance, watch that clip again. In fact, I actually even would suggest that you show it to a friend or family member and get them to think about it before they see what happens at the end. All right, well, moving along. I want you to consider this thought experiment. Being in an airplane and tossing something straight up into the air as the plane flies along. So this particular airplane is going to cruise along 600 miles per hour, let's say due west for the sake of the argument. And I want you to imagine throwing a bag of airline snacks straight up into the air. Where's that bag going to land? So, it could land in your hands, could land behind you, could land in front of you, elsewhere. So think about this for just a minute. There you are, you're sitting there, 600 miles per hour, that's fast. You're moving, you throw the snack straight up into the air. What happens to them? This is a little bit hard to figure out. I want to model this with a so-called ballistics cart. I've got a couple of these. I'm going to use the top one in this picture, and I'm going to show you a short video that I filmed just a couple of years ago. So the car is traveling at a constant velocity, and it then launches a ball vertically. This is going to model that type of problem. Okay, so we're going to take a quick look at this. All right, let's take a look at the video here. This was shot in Smith Hall. Give it a second to go full frame, and here we go. Look at that. In fact, it goes straight back into the car. I actually want to back this up a little bit, and I want us to take a look at this at a slower speed. So now watch this. I want you to watch the ball, how it maintains complete straightness above the cart the entire time. Now, why is that? It's because it's keeping pace with it. Now we're going to do this to the left. The ball is keeping exact pace with the car. That speed that I give it, it doesn't just suddenly go to zero. It doesn't change at all in the horizontal direction. The ball gets launched up. There it is. And lands right back where it ended up. I have to admit, I feel so powerful when I watch that. I love that video. Okay, so going back here, let's get into some of the gory details. Now, I did a little bit of video analysis of this. So there's a picture of it right there. And then on the right, what you're seeing right there is a still, it's actually, it looks like a still frame, but it is a, I applied sort of a little video editing on this with some graphing software, and I put a little dot on the ball for every frame of the video. And sure enough, you can see what's going on. There's a few things to see that's going on here. It's not remotely obvious. First of all, if you look at these, the blue dots represent the position of the ball. And specifically, it looks like as it's going up, they get closer and closer together. And they, in fact, are, vertically speaking. And the same thing is true coming down, except they're getting further and further apart. So the ball is accelerating, or I should really say decelerating, up as it is shot out. It gets slower and slower and then reaches apogee and gets faster and faster. Or another way to say that is it is decelerating the entire time. However, horizontally, it's maintaining a constant speed. Here, I have a graph of both of these. The blue dots represent the vertical position. The vertical position of the ball, whereas the red dots represent the horizontal position of the ball. The blue dots clearly show that it happens to be accelerating, negatively accelerating actually, or decelerating in the vertical direction. The red dots show that it's just maintaining a constant speed in the horizontal direction. Two things happening here. Let's go backwards again. So the ball moves to the right at a constant speed thanks to me pushing on the car. And the ball decelerates vertically thanks to gravity. Kind of fantastic, huh? Now, the most important part and why it lands back in the car is because the ball has that constant horizontal motion that I gave it. There's no reason for it to change. All gravity does is it makes it change vertically, but it doesn't affect it horizontally. Now, we're going to stop here for the moment, and in the next video, you're going to take a look at this experiment done upside down, and then we'll make some concluding remarks. Okay? See you soon.